Hi, I'm Akhilesh Kumar Srivastava from ABES Engineering College, Ghaziabad. In today's lecture, we will learn about how to compute the address of a 3D array element, wherein the elements are stored in the column ledger order fashion. So we'll first learn about how the addresses are computed. We'll do the derivations. We'll solve some of the questions. And finally, we will take a gate question to solve the address calculations in the arrays. Now, the structure of the three-dimensional array can be correlated with the cuboid-like structure, wherein there are three different dimensions. So if I assume that this is denoting the first dimension in the cuboid, and this denotes the second dimension in the cuboid, and this denotes the third dimension in the cuboid, then the column measure order suggests that the element should be stored in the third dimension first, and then followed by the second dimension, and finally in the first dimension. So if I have to store the element in the third dimension, I can assume that the dimensions will be like this. This is the third dimension, and in the third dimension, we have the first column. Similarly, in the third dimension, this is the second column, and in the third dimension, let's say this is the third column, and so on and so forth. But the third dimension is not a 1D like structure. Hence, it will be like we are cutting the bread slices, and the size of the bread slices will be u1 first dimension multiplied with the second dimension. Let's say a denotion that the first dimension is u1, and the second dimension is u2, and the third dimension is u3. Then the sizes of the slices that we are cutting will be of u1 cross u2. So if I separate these slices, this is the first u1 cross u2 slice. Let's take this one as the second u1 cross u2 slide, and this as the third u1 cross u2 slides. Similarly, we have many u1 cross u2 slides, and the counting of these slices will be u3 because the third dimension is u3. So we have first u1 cross u2 slide, then the second u1 cross u2 slide. Similarly, we have third u1 cross u2 slide, and so on and so forth. We will have u3 such slices. All these slices are actually the 2D arrays. So we can assume that we have u3 2D arrays of size u1 cross u3. If I assume that the first element is A1, 1, 1, and the address of this element in the memory is alpha, then while storing the elements in the memory, if I have to see the address of this element, it means this is A1, 1, 2. So this will be equals to alpha plus u1 cross u3. And this is alpha plus u1 cross u2, sorry. Alpha plus u1 cross u2 because the size of the first slice is u1 cross u2. So we will store all these elements, u1 cross u2 element, to go to the next element in the second 2D array of size u1 cross u2. Similarly, if I have to look at the address of this element, which is A1, 1, 3, that will be equals to alpha plus 2 into u1 cross u3. Why 2 into u1 cross u3? Because you must have stored the u1 cross u2 element of this slice, and then u1 cross u2 elements of this slice. Similarly, let's assume that we have some slice in between, and let's say this is the kth slice. Then the address of the first element in this kth slice will be equals to alpha plus k minus 1 into u1 cross u2. Why we are saying that this is k minus 1? Because if I am taking a 2 here, then the multiplier of u1 cross u2 is 1. And then if you're taking 3 here, then the multiplier of u1 cross u2 is 2. Similarly, if I'm taking a k here, then the multiplier of u1 cross u2 will be k minus 1. So once we have entered the this slice, the kth slice, this kth slice is a 2D array, and the elements stored in this slice is also column wise or in the column major order fashion. So if I'm storing this element, then all the elements of this slice, this column will be stored, and then we will come to this element. So in this way, if I'm assuming that this is first row, second row, third row, fourth row, fifth row, and so on and so forth, then the first column, second column, and third column, and so on and so forth. So there will be u2 different columns and u1 different rows. If I'm looking at this element, so this is actually equals to a, 1, 2, and k. Why the second dimension is getting affected? Because we are referring to u2. When we were referring to the third dimension, we were having the k as affecting the third dimension. So this will be equals to alpha plus k minus 1 u1 into u2 plus u1. Why plus u1? Because the total number of elements in the first row or first column is actually equals to u1. Similarly, if I'm going to the third column, it means I'm referring to the element a, 1, 3, k. This will be equals to alpha plus k minus 1 u1 cross u2 plus 2 into u1. Why 2 into u1? Because we must have stored the elements of the first column first and then followed by storing the element of the second column. Similarly, if I'm referring to an element a1 jk, it means I'm referring to the jth column somewhere here and the first element of the jth column. So this will be equals to alpha plus k minus 1 u1 u2 plus j minus 1 into u1. Why j minus 1? Because if I'm taking a 2 here, then the multiplier of u1 is 1. If I'm taking a 3 here, then the multiplier of u1 is 2. Similarly, if I'm taking a j here, the multiplier of u1 will be j minus 1. Now, if I'm referring to the element in the jth column, I already have referred to this element. Let's refer to this element. So this element will be a, 2, this element will be a, 2, j, k. So the address of this element will be 1 higher than this address. So alpha plus k minus 1 u1 u2 plus j minus 1 into u1 plus 1. Similarly, the address of element a3 j k will be equals to alpha plus k minus 1 u1 u2 plus j minus 1 into u1 plus 2, 1 higher than the previous one. Similarly, if I'm referring to some ith row in between, then the address of that element will be a I j k is equal to alpha plus k minus 1 u1 u2 plus j minus 1 u1 plus I minus 1. I hope you must have understood that why we are applying the I minus 1. So here in this all the derivation, we have actually assumed that the array indexes are starting from 1, and every element is taking 1 byte for the storage. So these are the assumptions that we have made. Now, since we have to find out the generalized formula, hence we will have to remove these assumptions. Now let's remove all these assumptions. So if I remove the first assumption that every element is taking n byte for the storage rather than taking 1 byte, then the entire quantity other than alpha will be multiplied with the number of bytes an element is taking for the storage. Another thing is that if we are assuming a general index, starting index, for example, L1 is to U1, it means L1 is the first, is the lower bound for the first dimension, and U1 is the upper bound for the first dimension. Similarly, lower bound starts at L2 and upper bound starts at U2 for the second dimension. And L3 is the lower bound for the third dimension. And U3 is the upper bound for the third dimension. In the then we can replace the I with I minus L1 plus 1, J with J minus L2 plus 1, K with K minus L3 plus 1. Similarly, the U1 and U2, which are referring to the size of the dimension, will also be changed. The size of the first dimension will be U1 minus L1 plus 1, and size of the second dimension will be U2 minus L2 plus 1. Since we are not using the third dimension anywhere in the formula, but if we have to find out the third dimension, so that will be equals to U3 minus L3 plus 1. Now let us remove all the assumptions here, and the formula will become alpha plus, we are replacing K with K minus L3 plus 1. Minus 1 is already there. We'll replace U1 with U1 minus L1 plus 1. U2 with U2 minus L2 plus 1. Plus J with J minus L2 plus 1. Minus 1 is already there. The dimension which will be multiplied is the first one, so U1 minus L1 plus 1. And then for the third dimension, we have K minus L3 plus 1, and minus 1 is already there. The entire quantity other than the alpha will be multiplied with the number of bytes an element takes in the memory. Now you can see that the plus 1 and the minus 1 will get cancelled out here, similarly here, and similarly here. So the final formula becomes alpha plus K minus L3 into U1 minus L1 plus 1, U2 minus L2 plus 1, and then plus J minus L2 into U1 minus L1 plus 1 plus K minus L3. This quantity multiplied with N. If I assume that the U1 minus L1 plus 1 is referring the first dimension, or the size of the first dimension as E1, and this is referring as E2, and this is referring at E3 as E3, then we can write the formula in even better way, or the simplified way, like K minus L3 into first dimension multiplied with the second dimension, J minus L2 multiplied with the second dimension, and then K minus L3 multiplied with no dimension, and then entire quantity multiplied with N. So this way we can find out the formula for, or this is the formula for the 3D array where the elements are stored in the column measure order fashion. So this is the address for A, I, J, K. Let's take an example, and let's try to find out the address for that. We're taking a very simple one. Let's take the base address of the array as 1000. And let's assume that every element takes 2 bytes for the storage. The array is like A 0 to 10, then 0 to 5, and 2 to 7. And you have to find out the address of element A, 6, 7, and let's say 6. Let's take here as 0 to 8. Now, here the first dimension can be written as E1 is equals to 10 minus 0 plus 1. So that will be 11. The second dimension E2 will be written as 8 minus 0 plus 1, that is 9. And third dimension E3 will be written as 7 minus 2 plus 1, it means 6. Now, after this, you have to apply these things in the formula. So the alpha, the base address is 1000 here. And then the value of k is 6. This is k. So 6 minus lower bound means 6 minus 0. It means 6. Multiplied with E1. E1 is 11. E2 is 9. And then J here is 7. It has been asked to compute the address of 676. It means the J is 7. So 7 minus lower bound means 0. It means 7. Multiplied with the second dimension, that is 9. And then the third dimension, 6 minus 2. The entire quantity multiplied with 2, because every element is taking 2 bytes for the storage. Once you will simplify this, you will be able to find out the address. Let me do it for you. So 1000 plus, so 6 into 11 is 66. So 66 multiplied with 9 plus 9 into 7 is 63. And then a 4 is multiplied with 2. So 66 multiplied with 9 will be 594. So we have 594 plus 63 plus 4, and this multiplied with 2. So this is 4 plus 3, 7, plus 4, 11, 7, 9, 16, and 6. So 6, 6, 1 into 2. So this will be 1, 2, 2, 1, 3, 2, 2. Now, this will be added with 1000. Hence, the address will be 2, 3, 2, 2. So this is the address of the desired element using the column measure order arrangement. So we have a question related to the gate as per the gate 1998 perhaps. So let me solve this question for you. So it asks that an array, a two-dimensional array is given as 1 is to 10 and 1 is to 15 of integers. Assuming that each integer takes one memory location in the array is stored in row measure order fashion, and the first element of the array is stored at location 100. So what will be the address of element aij? So it's a very simple question on the address calculation, where the lower bound is 1, upper bound is 10. Lower bound is 1, upper bound is 15 for the second dimension. So let us first find out the first dimension, that is equals to 10 minus 1 plus 1, it means 10. The second dimension will be 15 minus 1 plus 1, it means that will be 15. Here the base address is 100, and every element is taking 1 byte for the storage. So we are going to find out the address of aij. So this will be equals to alpha plus I minus lower bound multiplied with second dimension plus j minus first dimension, and the entire quantity multiplied with n, or the number of bytes. So 100 is the base address. I minus lower bound is I minus 1. This multiplied with E2, and E2 is 15. plus j minus lower bound, it means j minus 1. And if we multiply 1 with entire quantity, it will be same. So this becomes equals to alpha plus 15I plus j, and minus 15 and minus 1 will make it minus 16. So this becomes 84 plus 15I plus j. So I hope this makes sense, and we have covered the column measure order arrangement formula derivation, followed by the numerical on the column measure order, and then we have solved a gate question also. So I hope you can solve any of the questions related to the address calculation by yourself. Thank you.